Hello. So in the second part of lecture 4 about logistic regression, we'll actually write some code and we'll start with a practical application in a competition about user identification. Topic 4, as you see, is really very huge, and I encourage you to read part 3 about regularization and about pros and cons of logistic regression, about validation and learning curves. So I encourage you to read it yourself. But we'll start with applying logistic regression in a really interesting tasks. So I'm skipping these toy examples of applying logistic regression. We'll start with an actually really almost real world task. Okay, so in our course we have two Kaggle and class competitions. So it's a really very cool practice to go for Kaggle and to start building models, creating features, ensembling models. There are lots and lots of advantages of having some practice on Kaggle. Though in real world tasks, actually this modeling is about only 10 or 15% of a real project time. But still there are some applications where Kaggle techniques help very much, and our course is mostly for beginners, and at the beginning, when you just make your first steps with machine learning and maybe in your data science career, practicing on Kaggle a bit is really very helpful. So for such things as practicing feature creations, feature engineering, validation, all these tricks of cross-validation, this is, I would say it's the best source of practice for such things. So in our competition, in our course, we've got two competitions, and here in the first one, we'll apply logistic regression. So you'll see it works almost the best here. And some words about the task. So here we have user sessions on the internet. So users visit different websites. So it turns out they can be almost perfectly identified. So actually the task of user identification is a bit more complicated. So from all the crowd of people picking and identifying the right person, okay, this can be done by tracking websites. But distinguishing between one person or another, it's possible and almost can be done almost perfectly. Okay, so actually this sounds maybe too Russian, tracking the persons on internet, but actually many companies don't do that, but use some features like visited websites. They use it just as client features, or technically called, these would be embeddings, just features that can be helpful in your different tasks, like for search systems or for recommendations. So particularly in this task, we have very simple data set. So it's taken from a scientific paper, a tool for classification of sequential data. So we've got logs on servers, and we now only visited websites and timestamps, and from that we'll distinguish whether these web sessions belong to Alice or somebody else. Okay, so we'll pretty soon dive into this problem. Just a couple of words about Kaggle and the competition. So we've got data here on this tab. It's all described here, both in English and Russian. We've got kernels. It's very helpful. So people can share some ideas here. So you'll see that this competition is really interesting because you'll dive into visualization and feature engineering, and you'll come up with features that really work. And adding these features and seeing incremental improvements in your score is really very cool. Okay, so I've provided here a baseline with logistic regression, and then another baseline with correct time cross-validation scheme. So we'll first start with simple things, and then we'll take a look at this kernel about specific cross-validation for this competition. But you can share your kernels here, only that you're not allowed to share really high-performing kernels. So in assignment 4, you'll be beating baseline in this competition. So it's somewhere here, a logistic regression with 6 features. So this is the score. We'll discuss metric a bit later. But so please don't share a really high performing kernel. It's really very nice to compete here, and in assignment 4 you'll be beating this baseline, this baseline of TF-IDF and 6 features. So don't spoil assignments and competitions by sharing really high performing kernels. But otherwise, if a kernel is not really high performing, you can share some insights, visualize data, and share some findings that you see, whether features work or not, or don't work. So typically kernels are really a very nice source of in real Kaggle competition tasks, source of knowledge and actually sharing knowledge. Leaderboard. So typically in Kaggle competitions we've got public leaderboard and a private leaderboard. Just a couple of words about that. So the idea is that you've got a training set. This might be big, matrix X and vector Y. This is your train set, and you also have a test set. Test set might be smaller or larger, doesn't matter, but we don't have labels for them. So our task is to predict labels for the test set. For that you build a model. I would draw a small decision tree. So you fit a model on your training set. Okay, so this will be fitting. And then you make predictions for the test set. The idea is to build a model that's going to work with any type of test set, so for any future data that we'll see. And so for that purpose, actually on Kaggle, they divide the test set into 2 parts, public part and private. The idea is that if you tune your model and do lots and lots of attempts, you can overfit even for test set. So you can make such predictions that work on the test set, but they won't work, let's say, for another part, another test set. I would call it test 2. So some data set really very similar to the test set, but it differs a bit, just some data from another distribution. And if you make too many attempts, you'll fit to this test set, but your model will work much worse on the second test set. So for that purpose, Kaggle provides a public part of public part of the test set. So this is public, and another one is private. And when you make a submission, you'll see your score only on a public part. So actually Kaggle, organizers of competitions on Kaggle, have this vector of answers, Y test I would call them. These are of course hidden, so it's hidden from participants. And your task is to build a model and to make a vector of predictions. So here we'll have a vector of predictions for the whole test set. So this is a vector Y predicted, Y pred. So this vector is compared to the vector of correct answers, here Y test. But the result is reported only for this public part. So there's one part here public, and one part here, okay, this is public, and another part is private. So they compare your predictions and real answers only on a public part, and then Kaggle reports you back some score, let's say 09, some metric. We're not discussing currently metric, but let's say it's rock aug, and you get the result only for that part of the test set, only on a public part. The idea is that you get the scores only for public part, and in the end of competitions, something like 1 week prior to the end of competition, your scores on private part are revealed, and the idea is that your model needs to work on a private part equally good as on a public part of leaderboard. Okay, so here if we go to these competitions, we see scores only on the public leaderboard. It says that the leaderboard is calculated with approximately 50% of test data. So here the split into public and private is equal, though it's not always the case. And so private leaderboard, okay, it's accessible for me, but it's not accessible for you. So it's revealed only in the end of competition. And actually winners are typically, so winners have such models that perform equally good on private leaderboard. And okay, so private leaderboard actually defines prizes, and actually if you perform really well on public leaderboard, that doesn't often mean that you've built a good model. Maybe you've overfitted your model to this public test set. So the crucial part is actually the private score, which is revealed only in the end of the competition. Okay, so for assignment 4, you'll have to beat some baselines. This one. To simplify, for now, it's just to beat on public leaderboard. But we also grant more credits in our course in the end to the winners of these competitions. So this will be decided with respect to private leaderboard. Okay, so just a couple of words about this competition. And finally, the most important one. So if you want to get credits, you'll need to name your team in full correspondence with your name in course rating. So you can go to team. Yep. So your team is going to be a team of only one player. So here with God competition, it's really a lot of fun, but we don't allow team merges. So there's maximum for only one person in one team, and you here change your team name to match correspondingly with student rating. Okay, so if you go to the main site, mlcourse.ai, so we've got assignments, and these assignments will be accounted for in rating. And okay, at the point of recording this video, the rating is empty, but just take a look when we share the link, and your team name on Kaggle shall match ideally your name on the rating. Okay, let me spend just a minute so that I find this rating. Okay, so in a roadmap, all our activities are described in detail, and here's a link to the rating. As for the time of recording, it's empty, but you see you'll have some credits for Kaggle Alice. This competition, for another one, Medium, for 10 assignments, for projects, tutorials, and so on. And so you'll have your name here. Just make sure it coincides in your Kaggle team name. Okay, let's now dive actually into this competition. So first I'll provide some really simple baselines with logistic regression. First we'll get used to working with data, we'll understand the data, and then we'll take a look at a bit stronger baseline, and we'll discuss cross-validation for particularly this task. Okay, so here I'm importing libraries. I've got a small template. I'm not really very quick at writing code, so I'll have a small template and we'll continue writing code here. There will be a helper function to writing a submission file, and we'll actually do some submissions live right here, and we'll see how we can improve our score and how we can solve the task better. Okay, but first, reading data. So if you go to this competition, you've got data here. You can download it. Actually, you can work with in kernels, but I would say working locally is better. So kernels are not ideal for really heavy computations. And here we can see train sessions, test sessions, a sample submission, and we read our data here. We convert times into a special type for date times. Okay, so let's actually understand our data. So what's going on? We've got some sessions. These are browsing sessions, and a session is actually 10 sites visited in a row. So a sequence of 10 sites, and here we also have times. So the first session was site 56, visited at this timestamp, 12th of January 2013, 8 a.m. and so on. And then site 55 is visited at some another timestamp, and here we define a web session to be either 10 sites long or maximum half an hour. So here in the first session we've got only 2 sites, but let's say in the third one we've got 10 sites. So actually a user can return to some site twice or 3 times in a row. So actually some sites can be duplicated here in a web session. So let's say 946 was visited several times, so actually 3 times in this session. Okay, and finally the rightmost vector is our target, so whether it's some Alice or not. So we are going to do binary classification here. Okay, so for now we'll drop times and we'll work only with sites. I need to clarify that these are just site IDs, so 55 or 56 is just some site ID. So it stands for some real host name, for some real URL, but these are not numeric features, so these are only site IDs. And if we go to competition page, we've got a site dictionary, a pickle object that stores the mapping from IDs to actual site names. Okay, so the simplest approach will be to omit times and work only with sites. So that's why we'll take only sites. So features site 1, site 2, and blah blah blah, and site 10. We select these sites. If there is a missing value here, NA will fill it with 0. So 0 will stand for unknown. Convert it to int, and we'll transform the data with count vectorizer. Okay, let's dive a bit into this. How shall we work with such features as sites? To understand it much better, I encourage you to read this fourth part, logistic regression applied to text tasks. And here the idea of bag of words is described. So a really very simple approach to get features from text. And here we've got the very same setting. So we'll use the idea of bag of words. Okay, in a nutshell, we'll have these features site site 1 dots site 10, and we'll have our target variable, whether a web session belongs to Alice or not. Okay, and these site features are actually IDs. So ID of some site, let's say 17, then site number 62, and so on, then site number 105,134, doesn't matter. Okay, these are just site IDs. And if you think about it, a feature like site 1 is not actually a predictive feature, because we can shuffle this mapping from IDs to sites, and the feature will change in a drastic way, but actually there was no any reasonable change. So if we've got a mapping that, let's say, facebook.com, it's site number 1, and then mail google.com is site number 2, and so on, and then something like hockey.com, site number 117. If you think about it, if you change this mapping to another one, let's say Facebook now will be 117, if we just inverse this mapping, and this will be 116, and then hockey will be number 1. So if you think about it, then with such inversion, nothing really changed. We just switched site IDs, but these site features will drastically change, so that's why they won't have any predictive power. So instead we shall work with sites just as words, and we'll build a bag of words. So if we'll have a session like first site 117 was visited, then some site number 1, then site number 2, and again maybe site 10 in this session will be site number 117, and then target. Okay, so from this we'll actually build a representation called bag of words, or just bag of words. So we'll have separate features like site equals to ID number 1, and then dots, site equals ID 117, and then blah blah blah. So this will be really many features, and then site number maybe 10 to the power of 5. And for the first session, we'll just put number 1 here. So site 1 was visited once. So site 2 maybe was visited also one time. Site 17 was visited 2 times, and we put 2 here. So we'll actually, for the first session, we'll create this sparse vector of visited websites counts. So mostly this will be zeros, 0, 0, 0. So mostly there are no sites in this session except for 7 or 8 or maybe 10 sites. So this is a vector with really lots and lots of zeros, and efficiently it will use another format, sparse format, for this vector. Okay, so I'm not going deeper into details here. Just read this part about applying logistic regression for a text problem. So we'll see the very same idea as if we had words. So a long vocabulary with all possible words, and we mark the words that we see in current line with ones. So mostly this will be a vector of zeros. And here in this part we explain the idea of sparse format, and we'll also use it here. And again, in assignment number 4, there will be much more about this sparse format. Okay, so we'll transform our data using count vectorizer, which will actually build counts for all sites in our web sessions. Okay, I'll provide you with a small example. So we'll create a count vectorizer object, and let's say how it works with a session like this. I'll call it a web session with site 1 visited, then site 17, then site 2. Okay, so this is a small web session with 3 sites, and let's see how this count vectorizer will transform this data. We call fit transform. Okay, and we'll get a 3x3 sparse matrix. Okay, to make it actually better, I'll add one more session. So this will be session number 1, and the second one will, let's say, it will slightly differ. Let's say the second session will be site 2 visited, then again site 2, and then site 1. So if we transform this, one moment. So for this format, they shall be separated with spaces. Okay. Okay, we separate sites with spaces. Okay, one moment. So we don't need lists here, just strings. So with a bit of pre-processing, we'll have our web sessions in this form. So we'll just write site IDs, space separated, and we'll have some transformation for this. Okay, so I'll show you an example how it works with texts. So if we have 2 phrases, maybe we'd like to perform some sentiment analysis on that. So let's say we've got a couple of phrases like this movie is awful, and another phrase like enjoyed enjoyed this movie. What we'll actually do with this data, we'll build a bag of words for that. Okay, I'll draw how it will look like, and we'll apply the very same idea with sites. Okay, so we've got first string. So this movie is awful. And the second one, enjoyed this movie. With bag of words, we'll find all unique words in this whole collection. So there will be much more in a real task. There will be much more strings like that, and all unique words in this collection for now are just only 5. This movie is awful, and one more word, enjoyed. But in a real dataset, there will be lots and lots of unique words, and for each unique word, we will create a feature. So in this case, all unique words will be this movie is awful, and another word, enjoyed. And so a vector describing the first sentence will be just zeros and ones, indicating the words present in this sentence. So for the first string, this will be this movie is awful. So four times just 1. So with 1 we specify the word encountered in this string, and enjoyed wasn't there. So the vector 1, 1, 1, 1, 0 for the first sentence, and for the second, this movie, here we have zeros, and then enjoyed we have ones here, 1 here. And if we have multiple identical words in a phrase, then we'll calculate counts. Okay, so if we have a second occurrence of word movie here, okay, so not really interesting example, but enjoyed movie, this movie is blah blah blah. So for this phrase we'll have movie twice, is also twice here, once here, and so on. Okay, so that's the idea of bag of words, and in sklearn it can be implemented with the count vectorizer. Let's just see what's done here. So we feed this count vectorizer with these two strings and see what happened. So for now, not really interesting. So it's a sparse matrix, 2 rows and 5 columns. For sparse matrices, we can call 2 dens to get dense representation. And we'll see here that these are zeros and ones. If I change it, enjoyed this movie is blah blah blah, then we'll have 2's somewhere. And for this CV object, we also have a vocabulary. Okay, so this vocabulary says us that for word this we've got ID 4, for movie we've got ID 3. So actually this matrix stands for the very same thing that we've drawn here. Okay, so for movie it's number 2 in the second row, and here we've got it. Number 2 for movie is ID number, so column number 3. So here is this number, so these 2. Okay, so actually this is a sparse matrix. Let's call it X sparse. If you were to implement a sparse matrix yourself, you'll do a really simple thing. You'll just store your non-zero elements, because for a really long vector, so for a large number of unique words, you'll have something like that. 0, 0, 0, so mostly there are no words in this phrase. Then you've got 1, then maybe 2, again zeros. And this might be a vector of length 10 to the power 5. So suppose you were to implement an efficient data structure for that. So you'll just store this 1 at position number 3. So 0, this is position 0, this is position 1, this is position 2. Okay, you'll store number 1 at position 3, number 2 at position 4, and so on. And so actually it can be simplified only to something like a list or even a tuple with value 1 at index 3 and value 2 at index 4. Okay, so and SciPy's sparse matrix is actually something similar, but with lots of nice methods to calculate different expressions on that. And so actually sklearn supports sparse matrices. Okay, so I'll initialize it like this. So this is a sparse matrix. If you print it, it only says that it stores 8 elements in compressed sparse row format. So you can always call 2dens to print the whole matrix. But the idea is that it might be really very, very large, and printing it as a dense matrix will require too much memory, so be careful with that. And also this object has data, so you actually non-zero elements. It has indices where these non-zero elements occurred. And you can call non-zero to actually get all these non-zero elements. So first will be will be indices row wise, and these are indices column wise. So actually, if you compare it with actual data, now it's clear. So at position 0 and at row number 0 and column number 0, we got value 1, and so on. At row number 1 and column number 4, we got 2. So this is actually a representation of a sparse format. Okay, and we'll have pretty much the same with our sites. So we'll represent web sessions like this. And so this will be a sparse matrix containing the counts for visited websites. Okay, so these were some words about count vectorizer. So I'll actually delete this because this is nicely explained in this part about bag of words. And it will also be explained in much more details in assignment number 4. Okay, so just a bit of pre-processing to feed data to count vectorizer. We need to convert it into a format like this, where we'll have site indexes separated with spaces. So count vectorizer can read data from file, and in this case you can apply different transformations to your data frame, but maybe the simplest thing to do is just to convert it to a CSV file separated by spaces, and we fill missing values with zeros. This will stand for unknown website, and so this will be integers like this. So let's say the third web session is now represented as a string with these site IDs. Okay, now we feed data to count vectorizer, and we've got a train set with 250,000 observations roughly, and a test set with almost 83,000 observations. And 41,592 is the total number of unique websites in our data set. So it's really very similar to working with words. We'll save train targets in a separate vector, and now we can actually train some model on these sparse matrices. Okay, so we'll train a logistic regression on this data. And the idea is that, to first check your model on the training set, and then to make a submission to get the score on a public leaderboard. Okay, so we'll not only train a logistic regression, but we'll also perform cross-validation to see how our model works on our data. So we described cross-validation in detail in lecture 3. Okay, so we'll have a model, let's call it logit. It will be logistic regression, so I imported it from sklearn linear model, logistic regression. We'll leave all parameters as defaults. Only for reproducibility, let's fix random state. It can be any integer. I will place 17. Actually, the most important hyperparameter will be C, capitalized. By default, it's equal to 1. It's about regularization, so you can read about it in part 3. So regularization and cross-validations are covered here. So currently now I'm not going into detail, so we'll cover regularization with the regression in lecture 6. Okay, so these are actually parameters by default. And let's perform cross-validation. So calculate cross-val score. It's from sklearn model selection. What do you need to pass to cross-val score? Estimator, your model, your data, then scoring. So it will be a function. your metric, and cross-validation scheme. Okay, so we'll pass here logistic regression, our logit object. We'll pass here our train set, x train. This is our sparse matrix. We'll pass also y train. And for CV, we'll just perform 5-fold cross-validation. So it's not perfect. We'll discuss later that we need a much more complicated, not much more, but still a bit more complicated cross-validation scheme. And we need a metric. So our metric for this competition is ROCAUC score. So I'm not delving into details here, so you can read about ROCAUC score. It's a metric to compare predicted probabilities with actual binary labels like 0 and 1. Okay, so we'll calculate time needed for that, and we'll save results into something like CV scores. Okay, requires just some time. What's actually done? Logistic regression is trained 5 times on 80% of data, and we calculate ROCAUC for the remaining 20% of our train set. Okay, around 24 seconds, and we can take a look at CV scores. And typically you'll only care about mean value of CV scores. Okay, a typo here, sorry. Okay, CV scores. Okay, I'll do like this, CV scores equals the wrong value. Again a typo, sorry. Okay, CV scores. Okay, so actually it's very nice to take a look at these CV scores and to see how much it differs on different types of your data. So here we see that there is some variance, so it got only 83 on one part of data and around 92 on another part. So we'll have a better cross-validation scheme. But for now, let's say it's okay, and we'll calculate only the mean value as an estimate of the quality of our model on the training set, on cross-validation. Okay, now the second part, apart from assessing cross-validation quality, is actually training it on the whole dataset. We'll fit our model on X train, Y train. Okay, let's also take a look how much time it takes. Around 6 seconds, and we'll make a prediction for our test set. So Y test prediction with logistic regression, I would say index 1, so this will be the first prediction. We'll take a trained model, take predict proba, pass the test set, and predict proba will return as many columns as you've got classes. We've got 2 classes, 0 and 1, and we'll take only the second column. So we actually take care only about predictions for the class 1, so whether it's Alice or not. Okay, so here we've got our predictions, just some float numbers between zeros and ones, and we'll write these to a file. So we've got a special helper function to write submissions to a file. So we pass only predicted labels or probabilities. We pass file name. Okay, so if we call write to submission file, shift tab, and it says what we need to specify. So instead of predicted labels, we'll pass these predicted probabilities, then file name like logit submission1 txt, and other values can be left by default. Okay, we've written it to a submission file, and now we go to competition submit predictions, and we need to upload this file. So, okay, you don't see a special window, but I'm searching for this file that I just saved, submission 1. Let me see. Okay, so logit submission 1. I'm just searching for this file where I saved it. Logit submission 1. And it's a very, very nice practice to describe your submission and also to write here your cross-validation score. So it will be really convenient for you just to keep track of your submissions. So you describe it logit plus count vectorizer, or just bag of words for sites only. So we don't use times here. And we can write something like 5-fold CV rokauk was around 88.5. Okay, so we make a submission, and now we see the score. So it's about, here it is, 90.8. Okay, so it's much worse than we see in a baseline, this one, but still it's a first step. So we can keep track and try it. So with this submission we got around 0.908 rokauk. So this is the score on public leaderboard. So you can't currently know your private score. So this is your public part. Okay, and it's very helpful to have a separate, let's say, Google Doc where you keep track of your submissions. And you shall remember that for this submission you've got a CV, a cross-validation score, around 0.885. And now if you make some improvements to your model, and if you observe improvements both on CV score and on a public leaderboard, that means that you've done a nice thing, and it's going to really work on a test set. Okay, to make an improvement, I'll add some features, time features, and this is going to improve our model really very much. Okay, we don't, so apart from sites, we also have times, and okay, so people can behave in different ways. They can visit certain sites in mornings or evenings, or we can just keep track of an hour when a certain site was visited. This is going to be really helpful information. So our intuition is that Alice will visit, let's say, social networks or other sites like Google.com in specific periods of time. That can differ from others, and this can help to actually identify Alice versus others. Okay, and so here I'll create several time features like hour when the session started. Then I'll make some binary features like morning, day, eve, and night. And you'll see you can extract much more features from time, but I will stop at these 5. Okay, and we need to define what exactly morning is, what day is. Okay, so again, I'm not too quick at typing, so I'll copy these features from this baseline. We'll take a look at it a bit later. Correct time-aware cross-validation scheme, and we'll take features from here. Time features, they are defined in a special function. Okay, so I'm defining a function adding time features. So this will calculate hour. We'll take only time 1, so this is the timestamp of where the session started. Okay, and so morning will be from 7 to 11, day will be from 12 to 18, evening from 19 to 23, and night from 0 to 6. Okay, and so our function will take a data frame, our sparse matrix that we already built. It will take sites, it will extract features from the data frame, and now an important part will stack all these features together. So I'll draw it a bit. Sorry, I'll draw it a bit. So we'll have a sparse matrix with all sites. So this is a bag of sites, site 1, blah, 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 site 41k. So a sparse matrix with really lots and lots of sites. And we'll add 5 features. This will be our time features. 1, 2, 3, 4, 5. And we'll need to somehow glue these together. And we'll apply here horizontal stack from SciPy sparse. So this will take a sparse matrix, a dense matrix of time features, and this will produce again a sparse matrix with the result. Okay, so we need to pass here a list. The first element will be our sparse matrix with sites only. Then we'll have morning feature, day, evening, and night. We need to reshape them correspondingly. Okay, so this will add time features to our sparse matrix, and we need to apply it both to our train set and a test set. Okay, so our sparse matrix, but now with time features, will be the result of applying this function to our train set and to train date frame. Let me take a look. Yeah, you see we'll have a bit more features, and then we'll train our model on this new data. Okay, so we'll only fill missing values here with zeros, and now we can actually calculate the very same for the test set. Okay, sorry. So the test set with features will be applying this function to xtest and test date frame with missing values as zeros. Okay, this may require some time. Let's again keep track of it. Okay, while it's being calculated, I'm going to specify that it's really very, very important to use here hstack from SciPy's sparse. So I've imported it here from SciPy sparse. So we need to make sure that the result is also going to be a sparse matrix. Otherwise, it's going to be a dense matrix, and it will be really very, very inefficient to train logistic regression with a dense matrix with so many features. If you make such a mistake, you'll just see that you are running out of memory or it requires too much time. So we'll further train the very same model with these sparse features. Okay, so for now I'll only copy this code. So we'll make another submission. Okay, while it's being calculated, we'll do the same. We'll calculate cross-validation, but now with new data. Okay, something unexpected happened. Okay, I think it's calculated the first one. Xtrain with time. No. Okay, I'll just compare it with this result. Okay. Okay, so it's not really nice to struggle right now. Okay, so actually from this date frame we need only time 1, so we can actually pass a series. Time 1, this will be a series object, and we'll pass it here. Okay, let's change it a bit. So we'll extract hour from here, and at this point, okay, we'll need to take time 1 feature from train.df, and here time 1 here from test.df, and also fill missing values here and there. Okay, let's see whether it works for some, let's say, 5 first rows. Xtrain will take first 5 rows and all columns, and here we'll also take first 5 rows and then only time 1 feature. Invalid index. Okay, so let's debug it a bit. Hour, okay. Apply not found. Okay, let's take a look at this object. So we've taken time 1, filled it with zeros. Okay, so it's a session ID. We've got timestamps, and we'd like to apply a function to convert it to hours. Okay. We take our timestamp and convert it into an hour. Okay, and it worked. So we took timestamps and we created a feature hour. Okay, let's apply it to the whole time 1 feature. Okay, and so it worked. And the same for the test set. Okay, maybe it's a bit annoying that I'm struggling here, but I'm just showing you some debugging practices. So you can disentangle your function. You just take some piece. You can just test some special pieces of your code. So actually we can extract an hour feature from both our train set and test set. Okay, yep, sorry, now I see, now it's clear. I just missed my arguments. Okay, sorry for that. I need to specify, I need to pass this first series object as a first argument and the sparse matrix as a second argument. That's why I got these troubles. And that's why it's much better actually to name your arguments, to say that this is your argument time 1 series, and this is going to be your argument x sparse. Okay, so now we've passed a feature. Okay, we took first 5 rows. Okay. No, now it shall be okay. Okay, let's make it work for first 5 rows as well. Okay, I don't like debugging anymore. I just think that, okay, I passed the correct order here, and this shall be okay. Okay. Okay, so I've got Xtrain with time. Let's take a look at its shape. It's going to be the same number of rows and 4100 41,596 features. What we had previously, let's compare. Our previous training set shape was 49,592. We've got 4. Okay, again, strange. Why only 4? 4 features more. It should have been. Okay, it's morning, day, evening, night. Okay, we're not adding hour as an additional feature. Okay, so that's why 4 features more. And the same for X-test shape. It's going to be the same number of rows as previously, and now 4 features more. Okay, so I'll perform cross-validation again with this new dataset. Again, it will take some time. Then I'll fit the whole model with new dataset and make a second submission. This will be prediction number 2. Prediction number 2 will take X-test with time, and we'll make a submission, logit submission 2, and we'll fill in here our new values for cross-validation and for public leaderboard score. Wow, CV scores now 93, so much higher than previously. We can take a look at raw CV scores. So the variance is not as high right now. So we can write here that we've got 0.9307 cross-validation score. Okay, and now we've fitted a model with new data. We're making a new prediction. Again, these are just floats. We write it into a submission file and make another submission. Okay, now it's really important to tell what you made different. So we go again here to the competition page, submit predictions, choose another file. Okay, and now you'd better describe what you actually did. So you stick to the very same logistic regression plus bag of sites. But along with that, you also passed time features plus 4 binary features. Morning, day, evening, night. And now you've got CV score of about 0.93, and let's take a look what's the public leaderboard score. It's really intriguing. Woohoo! Yo! So it's 93565. Okay, so it's much better than our initial template, the baseline solution. Okay, so let's write it here that we've got on a public leaderboard 935.5. At this point, you better go to your Google Doc where you describe your experiments and conclude and write that your time features actually helped very much, and you increased your score both on cross-validation and on public leaderboard score by how much? By about around 3 or 4%. Cool. So if you've got improvement on your cross-validation score and on your public leaderboard score, that means that most probably this feature is really very helpful, and we expect that it's going to work on the test set. So it's a clear sign that you've improved your model. Finally, I encourage you to go to kernels and read about correct time cross-validation scheme, because here, if you try to fine-tune your hyperparameter C, so your regularization, you'll see that you'll have some discrepancy between improvements in your cross-validation and your public leaderboard. So you'll see that tuning your model on cross-validation won't help to actually make a better model. That typically it's a sign of not perfect cross-validation. So here we've got a time feature in our dataset. So these web sessions are somehow distributed over time. And so I'm not going deep into details. We'll discuss time series later. But the correct cross-validation in this case will be the one where our test set is always in future compared to the trained set. So if you perform this cross-validation, this will be much better. So because as well our test set is separated in time with trained set. So of course we are interested in predicting the very same but in future. So this doesn't mean that our model, so our task deals with time series. It only makes some restrictions on a correct cross-validation scheme. We always need to train the model on the training set and make predictions to the test set, which is separated in time. If you don't do that, you'll overfit to the training set. And I encourage you to read this discussion on Stack Overflow, right about this cross-validation scheme. Okay, in this kernel, if you perform right cross-validation, you can fine-tune hyperparameter C for logistic regression. It's regularization. We do it pretty much the same as we did it for decision trees in lecture 3. We specify a grid for different values, but now for continuous parameter C, and we'll take 10 values from 10 to the minus 2 to 100, 10 values in this interval. We'll perform grid search, and with that we'll get as much as 9, 4, 2, 4, and so on. Okay, and so performing right cross-validation will give you a much better signal whether you're doing right or wrong, and whether you'll just see that your cross-validation scores will correlate with your improvements on public leaderboard. Okay, that's now for it. In assignment 4, you'll have an obligatory part with filling in web form and with beating some more baselines. But you'll also have a more freely formulated part, so you'll have to come up to some more features and to beat these baselines that I've shown you. So now it's currently on 363rd place. This is really a clear hint that here we used logistic regression, TF-ADF instead of count vectorizer, and some 6 features. So you'll need to come up with maybe 3 more nice features and to improve your model and to actually beat your baseline. And don't forget to name your team of 1 member just in full accordance with course rating. So you'll see that it's really a very nice competition, that you can actually spend much time on that, but it's going to be fun. And actually, feature engineering is the best part of machine learners' work, and you'll see that it's really very cool. Okay, so good luck. Bye-bye.